So hello everyone. In this video, we are going to discuss about geometric versus arithmetic sequences. So the difference between these two sequences is on how they grow. The arithmetic sequences increase by a constant na amount. So suppose we have this explicit na formula, a sub n is equal to 3n. So with this explicit na formula, we can generate this sequence with the initial terms 3, 6, 9, and 12. So each number is 3 more than the last. So the 6 is the difference between this term with term 3 and term 6 is 3. The difference between 6 and 9 is 3. The difference between 9 and 12 is 3. Okay, so as you can see here, the difference between the term with the next is constant. Okay, so this will be of the form f of x equals dx plus a. Okay, wherein a is the constant amount that is being added to this term. All right, so the geometric sequences, on the other hand, increase by a constant na factor. So if arithmetic sequence increase by the constant amount, geometric sequence increase by a constant na factor. So suppose we have an explicit formula b sub n is equal to 2 raised to n. So we can then generate a sequence 2, 4, 8, 16, 32, and so forth. So we simply have the terms b sub 1, b sub 2, b sub 3, b sub 4, b sub 5, and so on. Okay, so then we plug that into this formula, 2 raised to n, and we generate these sequences. So is this an arithmetic or a geometric na sequence? So each number is twice the previous. Okay, so this term results from this term 4 results from multiplying this previous na term with 2. This term 8 results from multiplying 2 to 4. This term equals 16 is resulted from multiplying 8 by 2, and so on. So each number is twice the previous. So this is of the term a of r raised to x, wherein r raised to x basically refers to this explicit na formula, and the factor is a. Okay, so again, the arithmetic sequence increased by a constant amount. So we have this term, previous term, plus the constant amount a, but the geometric sequence increased by a constant factor. So we have this term, r sub x, and the next term will be multiplied by the factor a. So we have a times r raised to x. So again, let's have a deeper or more examples for arithmetic and geometric na sequence. So again, arithmetic na sequence is a sequence in which every term after the first term is obtained from the preceding term by adding a constant number. Okay, and the constant number that is being the difference of the two consecutive na terms is called as the common difference, or of AP, or the arithmetic na progression, which is commonly denoted by D. Okay, so that's the difference. So suppose we have the sequence 5, 9, 13, and 17. The common difference is 4. So if we take the difference between 9 and 5, and we take the difference between 13 and 9, take the difference between 17 and 13, and it will result to a common difference, which is 4. And from the previous slide, so basically, the sequence is generated by a constant na amount. Okay, grows by a constant amount, which is 4. And what about the sequence? We have 0, -5, -10, -15, and so forth. So we notice the difference is -5. So we have -5 then minus 0, negative 10 minus negative 5. So the difference is negative 5. Negative 15 minus negative 10, that will give us negative 5. So what about the sequence? We have x plus a and x plus 3a plus x plus 5a. So what will be the common difference? It will be 2a. So if we take the difference of x plus 3a minus x plus a, so the x will be canceled out, right? So 3a minus a will be 2a. So x plus 5a minus x minus 3a. So the x will be canceled out and we have 5a minus 3a, which will also result to 2a. Okay? So what will be the general term of an arithmetic sequence? So suppose we have the first term as a and d as the common difference of an arithmetic sequence. So then what will be the general formula for this arithmetic sequence? A plus d, a plus 2d, and a plus 3d, and so forth. So suppose a sub I, if a sub I, then for all integers I greater than or equal to 1, we represent the term of the sequence then as a sub 1 as the first term, a sub 2 as the second term, a sub 3 in the second term. And based on the sequence that was given, the a sub 1 is equal to a, right? The a sub 2 or the second term is a plus d, and the third term, a sub 3, is a plus 2d. Okay, so how did we compute for this equation? So where do we plug in this values? K equals or I equals 1, 2, and 3. Okay, and we as I have mentioned, we have this first term that is common. That is the common for all of the terms. Okay, so we vary on the second term, and we can see that how did we result to this second term? So for the first term, a sub 1, the second term to this expression is basically 0. For a sub 2, it's d. For a sub 3, it's 2d. Okay, and it's actually the difference between this I and minus 1. Okay, so if I is equal to 1, then we have 1 minus 1, and this will result to 0. So we will be left with a only. But if I is equal to 2, so we have a plus 2 minus 1 times d, and it will give us a plus d. And if the third term for a sub 3, we have I is equal to 3, then a plus 3 minus 1 times d, that will give us a plus 2d. So we have gotten the sequence from plugging in this values of I into this this formula, right? So do you see a pattern here? So we are the subscripts of each term is simply subtracted by 1. Okay, so by symmetry, we can then have a sub n as the nth term as a plus n minus 1 or n minus 1 times d for all integers n greater than or equal to 1. Okay, so let's have an example. Let us find the 20th term of the arithmetic sequence. 3, 9, 15, and 21. So here, what would be the first term? The first term is 3. And the common difference is 6. Okay, so we take the difference 9 minus 3, 6. 15 minus 9, that will be 6. 21 minus 15, that will be 6. Right? So what we want to find is the term number or the 20th term. So we have plugging that into this, we have a sub 20. So what is the value at the 20th term? So we will utilize the formula for the arithmetic sequence. A sub n is equal to a plus n minus 1 times d. So we have a sub n is equal to a plus n minus 1 times d for all n greater than or equal to 1. So what we are interested with is a sub or the value at the 20th term. So we have 3 plus, so 20 minus 1 times the common difference, which is 6. So we have 3 plus 114, and we are left with a value of 117. So it means that the value at the 20th term is 117. Okay, now let's move on to the geometric sequence. So the geometric sequence is a sequence in which every term after the first is obtained from the preceding term by multiplying it with a constant number, and is called as a geometric sequence or geometric progression. So the difference with arithmetic sequence, again, in the arithmetic sequence, there is a common difference, okay? Or the sequence is growing by a constant amount. But in geometric sequence, the sequence is growing by a constant factor, okay? So, or in some other textbooks, this constant factor or constant number being the ratio of any two consecutive terms is also called as the common ratio or of the geometric progression, which is commonly denoted by R. Okay, so we suppose we have this sequence 1, 2, 4, 8, and 16. So what is the common ratio here? The common ratio is 2. Okay, so we have 2 divided by 1, that will give you 2. 4 divided by 2, that will give you 2. 8 divided by 4, 2, and so on. What about for this sequence? We have the sequence 3, negative 3 half, negative 3/4, negative 3 over 8. So what is the common ratio? If you divide this term by its preceding term, so it is negative 1/2. Okay, and for this sequence, 0.1, and 0.01, and 0.0001, and 0.0001. So the common ratio is 0.1. So 0.01 divided by 0.1, you can verify it. The common ratio is 0.1. And if you divide 0.000001 with 0.01, so it's also 0.1, so on. So we have a common ratio between the term divided by its preceding term. Okay? So what will be the general term of a geometric sequence? So let A be the first term and R be the common ratio of a geometric sequence. So then the sequence or the geometric sequence that we have is AR squared, AR cubed, etc. So if A sub I for all integers I greater than or equal to 1, we represent the terms of the sequence, then we have A sub 1 to A sub 3 as the first term, the second term, and the third term, wherein based on this definition of the geometric sequence, we have the first term as A, the second term as AR, the third term as AR squared, and so on. So what pattern can we see here? Given the I na values, I is equal to 1, I is equal to 2, and I is equal to 3. So if I is equal to 1, we have A sub 1 and it is equal to A. And if I is equal to 2, we have A sub 2 equals AR. So we basically, or we simply subtract. The power is basically just subtracting these indices or this position of the term minus 1. Okay, so if I is equal to 1, we have A sub 1, then we have AR raised to 1 minus 1. So that will give us a 0. This will result to 1, and it will evaluate to A only. If I is equal to 2, we have A sub 2, and we have AR raised to 2 minus 1, and that will give us AR. And if I is equal to 3, So we have a sub 3, and then we have a r raised to 3 minus 1, and that will give us ar squared. Okay, I hope you understand that. So we have a sub n is equal to nth term equals ar raised to n minus 1 by basically subtracting 1 to this subscript. Okay, so for all integers n greater than or equal to 1. Okay, now we have this geometric na sequence 4, 12, 36, 108, etc. So we want to find the eighth na term. So the solution would be to identify the first term, the common ratio, the term number, and determine or write down the term notation. Okay, so we have a as the first term, which is equal to 4, and the common ratio. So you simply divide 12 divided by 4, 36 divided by 12, and we can see that, let's see, we can see that the common ratio is 3. And what we are interested in is finding the eighth na term. So the n will be the term number equals 8, and the value at that term number, a sub 8. So assuming we have, or actually we have this equation for the geometric na sequence. So we have a sub 8 equals 4, which is the common ratio. The first term, I mean, a is equal to 4. And then we have the common ratio r, which is equal to 3 raised to n minus 1, wherein n is equal to 8. So we then have 8,748. So it means that the value at the eighth term is 8,748. So what are sequences in computer programming? So an important na data type in computer programming consists of finite sequences known as one-dimensional arrays. So a single variable in which a sequence of variables may be stored. So an example may be the names of the K students that may be represented by an array of K elements named as name of 0, name of 1, name of 2, name of K minus 1. So